Okay, so let me just sketch out the states we have here. It's always good to do that. And I always draw it too small, so. Five minutes, oops. And what do I have? I have a little resistance heater here. 2 amps go in at 120 volt source. And over here we've got 0.5 cubic meters and 2 at 400 kPa and 27 degrees C. Over here, the only thing we know is that we're still at 400 kPa, right? Because it is a constant pressure process. Nitrogen expands at constant pressure. Oh, we also lost heat. Let me draw some heat loss. 2,800 joules. So the overall energy balance is just energy in minus energy out equals change in energy of the system. So what kind of energy do we have? Well, we have energy coming in the form of work, and we have energy leaving in the form of heat and work. So what's happening here? Coming in, we've got the electrical work. So I'm going to say work. I'll use a E for electrical. So that's into the system. Remember, work in, heat, or sorry, heat in, work out. Let me see. Oops, you know what I did? I reversed the signs, didn't I? Oops, hold on. Yeah. All right, let's do it this way. Yeah, we have work in, and our work out is, we have boundary work, right? Because this piston is moving. So I can just make a little arrow here, right? In that 5 minutes, that piston is moving upward. So that's boundary work. So yeah, heat in, work out. And then we have heat out. Now, we have delta U and no delta kinetic energy or potential energy. Right, so there's no change in potential energy or kinetic energy of the system. It's stationary, it's just sitting there. So we can rewrite this U. Well, we can write the whole thing. For a closed system, right? For a closed system, at quasi equilibrium, expansion or compression for a closed system. I guess this should technically be and's not the best, but I put at when it should be. For a closed system, undergoing or and quasi-equilibrium expansion or compression at constant temperature or pressure, sorry, geez, we're at constant pressure. We have the following relationship, right? We have delta U equals the boundary work. Oh, sorry, delta U plus the boundary work equals delta H. I can't read my own handwriting, which is a problem. So we can take the boundary work and we can put it in on this side of the equation and replace this with delta H. So we can wind up with the electrical work minus Q out equals delta H. And then delta H is going to be M H2 minus H1, which for an ideal gas, we can write M CP T2 minus T1. So here we have the formula that we need to solve this, well, to at least start solving this. We've got electrical work in, heat out. That's going to be equal to the mass times the specific heat of the gas times the change in temperature, right? We don't know the final temperature, which is what we want. We want to solve for T2. So we got to figure out how we're going to get all this other stuff. So some of the assumptions for this, which we already kind of made the first one, N2 is an ideal gas. Again, I already mentioned this one. System is stationary. PE and KE are equal to 0. So these are all the assumptions so far that have gone into, what is it called? Reducing this equation. And then pressure is constant, right? That's not really so much an assumption as that it's given to us. So this is all the information we got just from looking at the problem and understanding it. So these are the inherent assumptions that we've made already. We can also assume that the CP of nitrogen is constant at these temperatures. Oops. All right, so the first thing we got to do here is we got to figure out these other terms. I mean, Q out, we already know. Q out was, did I even write it down here yet? No, I didn't. 2,800 joules. But let's figure out what the work, the electrical work in. So the work is basically energy, right? Work in is total energy in. Now, what are we given? We're given reserve, we're given power, or excuse me, we're given current and voltage. And what we know about current and voltage is power is current times voltage, right? And we're given the time that this is run for, 5 minutes. So we also know time. Power is also work over time, right? Let's first focus on the IV part of this term. let's see, we have, well, you know what? I'm just going to rearrange this all, and I'm going to get, I should have labeled this WE. WE equals IVT. So current voltage times time. Now the units on this, time has to be in seconds. This is in volts and this is in amps. And we were given 5 minutes. So let's just write this down here. We've got 2 amps, 120 volts, and I'm going to just I'll put the whole thing in here, the conversion. 60 seconds per minute. And then, how many joules do we have? Oh, yeah, this is volt amp. I forgot about this. There's a conversion factor in your textbook. 1 kilojoule is equal to 1,000 volt amps. I mean, a volt amp is basically just a joule. So we're going to just convert this into kilojoules. So we do the math here, we wind up with 72 kilojoules. So what do we have now? We have the work in minus the boundary work out. Yeah, it's up there. So work in minus boundary work out. Oh, sorry, boundary work we lumped over here. We gotta look at this equation. Work in minus heat out. So work in 72 kilojoules, Q out is 28 or 2.8 kilojoules. So now we're left with 72 kilojoules minus 2.8 kilojoules equals, now we have some unknowns. We have the mass of the nitrogen, we've got the CP, and then we've got T2 minus T1. Start a new page. So what's the mass of nitrogen? Well, the only information we're given here initially is pressure and temperature, right? We're not given a specific volume, but we're treating nitrogen as an ideal gas. So we can use the ideal gas law to find out the mass. So the mass of nitrogen from ideal gas law. And again, your text uses instead of using moles, it uses the mass basis, P1 V1 over R T1. And this R, what's the table in your textbook? Where'd my reference table go? There it is. Oh, I never jot down the table. It's table A, is it A2? Let's see, 97, that's nitrogen, yeah, 6.8. What's this table do? It's reported, oh, it's reported the same, I rounded. All right, so table A, you can use table A1 or A2. A1 or A2. Both of those tables have the gas constant for nitrogen in them. Table A2 also has a specific heat. R for nitrogen is 0.2968. Yep. And that the units on this are kPa, meters cubed, kilogram, Kelvin. So this is actually at the bottom of table A1. Remember, this is the one where they report the gas constant in units of kilojoule per kilogram Kelvin. And there's a little asterisk there, and you have to go down to the bottom and say, oh yeah, this is the same thing as kPa, meters cubed, kilogram Kelvin. You know, there's really no, I don't know why they reported it in kilojoules. You know, there's really no reason to do that. Typically, you use the gas constant in the context of pressure and volume. So I don't know. I really don't understand the reasoning why they did that. All right. We know the pressure, we know the volume, right? We're given 0.5 cubic meters. So let's just jot this information down. P1 equals 400 kPa. V1 was 0.5 cubic meters. T1, what is T1? Well, T1 is 27 degrees C. However, oh, my camera is, there it is. However, we need to use, when we use the ideal gas law, we need to use both absolute temperature and absolute pressure, right? So we have to convert this into Kelvin. We're just going to add the 273 to it, 300 Kelvin. I'm going to forget about the 1.5 on there. All right, so we can find the mass of the nitrogen. Why is this crooked? 400 kPa, 0.5 meters cubed. We've got, I'll put the gas constant 2968 kPa, meter cubed, kilogram, Kelvin, 300 Kelvin. I changed my gas constant slightly, so 400 times 0.5 divided by 300 divided by 0.2968 gives me 2.246 kilograms of nitrogen. And this is the point where you say, what were we doing with this number again? Yeah. So remember, we're solving for temperature 2 here. And I didn't write down the CP. The CP is going to be, let's see, CP of nitrogen, 1.039. And this is in kilojoule per kilogram Kelvin. And this is also table A2. Did they have this at A1? No, they don't. This is A2, table A2. 1.039. So now we can rearrange this and solve for T2 and find that T2 is basically, we've got 72 kilojoules minus, what do we got? 2.8 kilojoules. Uh-oh, did I subtract 28? To check my numbers now. Divided by MCP. So we've got 2.246 kilograms. CP is 1.039 kilojoules per kilogram Kelvin. I would just say, when in doubt, work in absolutes, absolute temperatures. And then we've got to add to it T1, right, which is 300 Kelvin. Because this is going to give us a temperature in Kelvin. So we need to add to it in Kelvin. What did I get here? 72 minus 2.8 divided by 2.246 times 1.039. Oh yeah, that's close. 29.65 plus 300 These are both Kelvin. So T2 equals, we'll round this to 329.7 Kelvin. Move that up. And that's going to equal, let's see, minus, oops, 329.7 minus 273. Just 273, because I didn't use the 1.5. We got 56.7 degrees C. So that's our temperature. T2. That's our answer for this problem. So that was basically looking at the energy balance, right? Converting, we knew how much work was going into the system. We knew how much heat was leaving the system. And we knew, so we knew energy in and energy out. And so the delta E of the system, in this case, the only trick here was recognizing that internal energy for a closed system at quasi-equilibrium and expansion or compression at constant pressure, this relationship holds, right? That the internal energy plus the boundary work is the enthalpy. And then from there, we can just plug in the MCP dt for the enthalpy and treat nitrogen as an ideal gas. And that's how we found the mass. And that's how we get to the temperature. All right, any questions about this particular problem here? All right, I'm going to assume that everyone watched the videos on internal energy or section 4.5. Let me just make one. I'll just pop back to the PowerPoint for 1 minute here. Internal energy change. Oh yes, for small temperature intervals. Yeah, I guess the point here is that for solids, right, CV and CP are pretty much the same, and your energy balance is going to be just simpler because you have a constant, constant CP or CV. They're both the same, right? And you can use the average, CP average. And did they actually give you the information here? Iron. Oh, that might not be. That's probably the piece of information I need to give you. Yeah, that's going to be in the appendix. All right, so what I'll do is I'll take a screenshot of this and have you guys work on it on your own. And then we'll go over it because it should be a relatively simple problem. Part of it is just figuring out where to get the data from, which I'll give you the table for that in a second. Properties of solids, 886. All right. Copper. Let me just make sure the numbers I've got. Yep. Iron. Where's water? Make sure water's here. Water. Here it is. No. Solids. Foods. Foods are in here. Well, there's liquids. Water. Okay. Is that the same one I used? Oh. 4.18. Okay. All right. Screenshot. That's what I was doing. Huh. That's weird. Getting all these errors today. Let's hope this works. All right, let me go to the screen and chat here. Put that in there. All right, now the other thing you need to know is, so let's look at this. A 50 kilogram iron block, right? at 80 degrees C is dropped into an insulated tank that contains, and it, I mean, it doesn't look insulated, but it is. This is like a super insulative glass. That contains 0.5 cubic meters of water, liquid water, at 25 degrees C. Determine the temperature when thermal equilibrium is reached. So you will need to know some information from table A3 in your textbook on the properties of water and iron. They also have a little subtable on that, properties of food. So you can find like specific heat of apples and bananas. That's exciting. All right, so why don't you guys take maybe 10 minutes to work on this, and it probably shouldn't take that long, but then we'll come back and see what you guys figured out. So I'm gonna set up breakout rooms here. Might as well do 2 of these because we've only got, oh, where's my breakout room?